Okay, so I'm going to talk about the operators. This is the most interesting topic and provide a new way of the MATLAB programming. Unfortunately, this topic is a bit tough, and you are able to understand this topic on the solid basis of the programming logic learned in the previous model, such as loop structures and if-else statement. Please review the previous topic carefully before starting this topic. When you use the operator in MATLAB, you can significantly shorten your code and reduce the number of the loop statements. At the end of this module, you can describe what is a vectorizing coding in MATLAB. You can use the operators when different combinations of the scalar, vector, and matrix are involved. Redesign the loop-based script using vectorization code. Apply this concept to solve the example in the previous model. Okay, so MATLAB is optimized for operation involving the matrices and vector. Okay, for instance, A is a, B is a, you want to do the element-wise multiplication. What you can do in the first, you can design the double loop structure. Like this. And then you're doing this element-wise operation. Or you can use this dot multiplication operator. Okay. In this case, the operator, this dot multiplex operator support the matrix and matrix for the element-wise operation. Okay. The point is that these long lines of the code script can be shortened like this, the simple one line. That is the beauty of the operator. That is a vectorization. Okay, vectorization is to revise the loop and the scalar-based codes to the code that involve the vector and matrix operation. Okay, it's like a matrix and the vector operation. Why is it better? The script is much more readable. And then take a look at this code. This code. Which one is better? I prefer this, right? Here's another example. We are adding the 3 on the elements in the vector. Following to the basic process that we learned in the loop statement, we read the individual element and then compute the value in the expression part and in the assignment statement, and then resulting value to assign to the corresponding location, right? However, MATLAB supports the syntax like this. What it means is the plus operators support the operation between the vector and the scalar. Okay, that's the operator. What is this operation? Element-wise addition. Okay. Again, you should understand this. What is this one? It's a 7, right? It's easy because it takes the same syntax as a mathematic operation. What about this one? This syntax does not exist in math, but there is a MATLAB. MATLAB predefined this operation. How? When you use the vector and scalar, MATLAB defined this operation as element-wise operation with this scalar. Okay, this is not math. This is a new syntax in MATLAB. Okay, here the plus is operator, and then this operation is defined when the vector and the scalars are involved. Okay? So we have learned several operators encompassing the basic numerical operator, dot operator, logical operator, relational operator. All of them are operator. When two values are provided left and right hand sides of the operator, they produce a single value, vector, or matrix. Okay? You might be familiar with some syntaxes looks like a math equation. It's like this one. However, this is a programming script. MATLAB defined how to compute the resulting value using the operator when the different types of or the size of the inputs are provided left and right hand sides of the operator. Okay? I only show the limited use of this operator between the specific variable type. For example, this equality, I only show the the scalar and scalar, right? But MATLAB support that it can be used for scalar and vector, or the vector and vector, okay, of which operation is already predefined in the MATLAB. This model is to show the what operations are conducted in this combination and how we can use those operations and then why they're useful. Okay, let's start with reviewing the previous model. Scalar and scalar operations are obvious, right? This one. This is the 12, 20, because this is similar to the exactly same with the mathematical equation. Okay. What about this one? When the scalar is involved, that is element-wise operation with the scalar, right? S1 is a plus in the each element in the V1. Okay. What is this? Okay, this one is the same when the matrix is involved. So that's why in here, this drawing, this text, this one is indicating we are putting in operator here, and this one is the combination of the scalar and scalar, vector and scalar, matrix and scalar. Okay. What is this, the caret operator? For instance, S1, this one become 100, right? 10 to the power of 2. What about this one? That is the element-wise, this is power of S2. For instance, here, this one is to become 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, 4 to the power of 2. However, what is this one? Without dot, that is the matrix multiplication. Okay, this is the equivalent to the V1 multiply V1. Okay, what that is the matrix multiplication. To do the matrix multiplication, the inner dimension should be matched. But this one is 1 by 4, 1 by 4. That's why this inner dimension is not matched. That's why there's an error. Make sense? Okay. How about this? It's an error? No error, because M1 is a square matrix. 2 by 2, 2 by 2, inner dimension is a match. There's a result value. Does it make sense? Okay, how about the multiplication between vector? Okay, V1 and V2. V1 is a row vector, V2 is a column vector. So 1 by 2, 2 by 1, that's by scalar. V2 is a 2 by 1, V1 is 1 by 2, that's why resulting is a 2 by 2 matrix. How about the M1 times a V1? M1 is a 2 by 2, B1 is a 1 by 2. That's why there's an adder. Okay, what about this one? This one is a summation, is element-wise operation, right? M1, M2. This one is just a multiplication. M1 is like a multiplication between matrix, this case. Okay. What is this one? This one is M1 times M1. Okay. That's why this M1 is not square matrix. This one is producing error. Okay. Okay, so what is the backslash? We saw this operator in the division between the scalar and vector or matrix. When we use the backslash between matrix, that's a matrix division. Matrix division. It's not just a simple dimension. Okay, a division. Okay, it's not a numeric division. Okay. Okay, that's the identical to the matrix multiplication of the M2. Okay, M2 backslash M1 is the same with M2 times inverse of the M1. Okay, so here the multiplication and then division is all these are like a matrix operation. So like A times B equal to C, and then let's say we are multiply the inverse of the B on the both sides, inverse of the B, and then this is identity matrix, and then cancel out. A is equal to C times inverse B. Okay, that is the same with A is equal to C backslash B. Okay, so if you see this equation and this division operation is simply like a simple math equation, like A times B, so that's why A is C backslash B. But the underlying operations when these ABCs are matrix, that is the matrix division. So this one is the same with the C times inverse B. Okay. In MATLAB, when you use this operation, there's a flag. So please use the, let's say, matrix division instead of the inverse function. But for me, I prefer this because it's much more readable rather than this. Okay, but it's your choice. Either one is fine. Okay. What about the dot operation? As we already learned about this, this is the element-wise operation. Element-wise operation. Okay. So there's a two vector v1 and v2. This one give you this, right? 1 times 1 is 1, 2 times 2 is 4. Then v1, the multiplication of the v2 transpose, that is this one and 2, 1. That's why it's a 2, 2. Okay, this is the element-wise division. Okay, matrix is also same. M1 is a 2 by 2, M2 is a 2 by 2. Element-wise, the multiplication and division. Okay, this. Okay, what about this caret operator? That is the power of the S1 for each element in M1. Okay, so it's nothing special. Okay, this is the matrix multiplication. Okay, M1 1 is 1 times. Okay, makes sense. So when you're using this caret operators, So you need to be careful to putting a dot or not. Those two are the totally different result. Okay, so we'll learn about this relational operator, right? This operator is to compare the two value, larger or less, or equal to or not equal to. Okay, so simply if you see this example, S1 is S2 is equal, no, that's what, false. Right? All this is the logical value. Okay? S1 is not less than S2, yes, that's very true. Okay, we can use this operator between the vector, and scalar. Okay, how that work? This is also the element-wise operation between the each element in vector or the matrix and scalar. Okay, so see this example. V1 is this one. S1 is a 1. 1, 1 is equal. Yes, 1. 1, 2, 1, 3, 1, 4. All the not equal. That's why false. What about this one? V1 is less than or equal to S2. S2 is a 2. 1 is a yes. 2, yes, no, right? V1 is not equal to S2. Yes, no, yes, yes. Okay, can you get it? And also, we can use this operator between the vector. Okay, to do this, the dimension between these two vectors must be the same. So like a element-wise operation. This is the same with element-wise operation between the vector. Okay, so if you see this array, V1 and V2 are the same in this location. Yes, no, no, yes. That's why you will get this vector. V1 is larger than V2, larger than or equal to V2. Yes, 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 yes. That's why you get this vector. Okay? And common mistake is this. V1 equal to V2. This is not a checking the equality. Not checking the equality of the V1 and V2. Okay? You need to use the syntax like equality. Is equal is a built-in function V1 and V2. Because this one is the element-wise operation. It's not checking the two value. Okay? It's the element-wise operation. That's why the vector, the outcome is the vector. It's not the single logical value. Okay? So please don't be confused. Okay? This is a very common mistake. Okay, we can use this operation between the matrix and scalar. Okay? And matrix and matrix. Okay? See here, S1 is equal to yes. Yes. This one, yes. No, 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 right? This one, M1 is equal to S2, not equal to S2, yes. No, yes, yes. Okay. Similar to the vector case is this relational operator between the matrix is the same with element-wise operation. Okay, the operation is a relational operation. So M1 is equal to M2. Yes. No. No. Yes. You will get this one. Okay, similar to the vector case, this one is also the common mistake. Why? This is the element-wise operation. This is not giving logical answer. Giving a logical answer, yes, true or false. Okay, makes sense. The output is the matrix, logical matrix. Okay. Okay, similar to the relational operator, we can apply the logical operator under the different combination. We learn about the logical operation between the scalar. This one, yes, no, because there's a zero, there is this, oh sorry, S1, yes, yes, that's why, yes, no, 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 yes or no, that's why, yes, right? Do you remember that? We can do this process between the vector and vector, matrix and matrix, and matrix or vector and scalar. Okay? But here's the one difference. When you involve the vector and matrix on this logical operation, you need to use the single and an OR operator. Okay? In the previous case, in this case, you need to use this double OR, double AND. But if you involve the matrix or vector, you need to use just a single symbol. Okay, so let's say this example, M1. Now here's M1, and then S1 is a 1. So OR operator, so there is at least a 1 in this comparison. That's why you'll get the full 1 matrix. Right? What about this one? M1 and M2. So the element will be 1 when both elements are 1. Otherwise, 0. So that's why you get this. Makes sense? Let's solve the comparable example. This question is to write a script to count the number of phi from vector. So when you see these problems, you need to be prepared to write a script right away using loop statement. Okay, this is the script using loop statement. Loop range is a set of the 1 to number of value, read the value, test if the value is a 5 or not. If yes, increase the num by 1. Okay, can you get this? Okay, how to solve this problem using operators? The key idea is you can directly check the equality using the equality operators for vector and scalar. Okay, here equality 5s give you a logical vector where true is located at the 5 in the vector, otherwise 0. Why this equality check the 5? Each element that 0, 0, 0, 0, 1, right? So you will get this index vector. Okay? These operators check the equality in each element in vector with a 5, right? So how to get the numbers of the 5 from this index vector? We can simply solve all the elements in this index vector. So num5 is the sum index. Okay, so if you compare these two scripts, you can significantly shorten the operation, and this script is much more readable and clear. Okay, but right now, so you might not familiar with this script at this time, because you're new to this operator. You'll see the value of this script. Okay, Bulls and cow problem again. I'm sure that you already knew this problem, right? Okay, how to write a script to compute bool. This is the loop-based solution. So read the value from the x true and x test at the same position, and if the same, increase the number b. Okay, so at the end, in this case, num b equal to 1. Okay, how to solve this using operator? These two vectors are the same size, right? So this task is to compare the value at the same location to see if it's the same or not. So in this case, you can use this equality operator. Okay, what is this one? Element-wise equality check between two vectors. Okay, so what is the same vector? That is a logical vector. 0 means these two values are not equal, but this one is equal. There's a 1. It's a true. Okay, and these are all 0. Okay, what is the num b? Just the summation of the same vector. And then num b become a 1. Does it make sense? When the two vector has the same size, this equality operator, perform the equality check the two number at the same location. Okay, so basically this one is achieved by this loop solution, but you can make this instead one line. Okay, so if you get familiar, for me, I write a script like this. Without introducing the same variable. Okay. So this one is a shorten in one single line. Okay, make sense? We are going to learn about another indexing method, that is the logical indexing. Logical indexing is to index array using the logical vector. So logical index vector, logical vector. Okay, for instance, if we access the second and third element, let's say second and third element, we are using 2, 3, right? This is index vector, right? It give you 1, 3, right? In this case. Okay. However, logical indexing is to use a logical vector to access element. Okay. One location are read or access the value, 0 are not doing anything. Okay. For instance, here you're trying to access the first and third element. You're placing this logical vector. Place this logical vector. Then one location read or access. In this case, a reading, right? Then this v2 give you the 4 and 3. Okay. Makes sense? Okay. Basically, you can use any size of the logical vector smaller than the numbers of the element of a target variable. For instance, in V1 is a 1 by 4 vector, and thus the logical vectors can be or should be smaller than the 4. Okay? For instance, in this case, logical vector indexes become like logical like this. It should work. Okay, this will give you the 4, 3, because this index vector is smaller than the the 1 by 4, which is the number of elements. Okay, but I highly recommend that you're using the same size of the logical vector. Okay, so in this case, I recommend the 1 by 4, but either one is fine. Okay, so main difference is in the previous case, the subscript indexing and linear indexing, the index vector include the locations of the value that you're going to extract. It's like a 2 or 3. But in this case, this logical vector contain the true or false. The true location is the number that you're going to read or access. Okay, that's the main difference. Okay, let's solve this 3 problem. Find the numbers more than or equal to 10 in vector. Okay, and not equal to 5, larger than 3, less than 7. Okay, before you start, as I said before, you should be able to write this script using the loop and then selection statement. To solve this problem, you're going to use the relational operator to vector and scalar. Okay, so let's take a look at this line. Vector is a vector, right? This one. And this is the scalar. In module 1, we only learn about the relational operator between the scalar and scalar, right? Like this, right? But this one is the vector and scalar. This is the element-wise operation. So if you do this, this will give you the 0. This will give you the location where the condition is true. That is that this one, otherwise a 0. Okay? So this is the key part of the logical indexing. Okay? This is a logical vector. We directly putting in this the indexing vector, and then you can read this and that value, and then we Q1 become like this. The other example is can be solved in a similar way. So vector is not equal to 5. That give you this index vector. You can directly plug in to the vec, and this give you the number at this true location. That is 4, 5. ID. Here. This one. Then the location. It's all value except for 5, right? Then this one. You can design this like a multiple condition statement. Okay, so here vector 3 is okay. Let me. Okay, so first term is vector is larger than 3, right? There is here's the vector 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, right? That is this term. And this term is a vector is smaller than 7. That is 1, 1, 1, 1, 1, 0, 1, 0, 0, right? And then told you, as I mentioned before, this is the the AND operator. But when the vectors are involved, you need to put only the single AND. Okay, this is for scalar. This is for vector. So if you do the AND operation, 0, 0, 1, 0, 1, 0, 0, 0, 0, right? That's why it only give you this value and this value. So you'll get this. Do you understand this process? When you make this solution, and then please compare this solution with the script using the loop and then condition statement. Okay, then you will see the value of the vectorization. Make sense? Okay, good. Okay, this is an optional topic. I would like to clarify the output form from the linear and logical indexing. Okay, first, output of the linear indexing and the logical indexing is always a vector. It's not matrix, although the target variable is the matrix. Okay? The question is it the row vector or column vector? Okay? When the input array is a row vector, then regardless of the linear indexing or the logical indexing vector is a row or column vector, output vector is always a row vector. Okay? It doesn't affect of the form of the linear or the logical indexing vector. Okay? But when the input is the matrix, if the linear indexing or logical indexing vector is a row vector, the output vector is a row vector. Okay? If this one is the column vector, output is the column vector. Okay? So let's take a look at the example. V1 is the row vector. V2 is the column vector. Okay? And then if you, okay, this is the row logical indexing. This is the column logical indexing. Okay? What is this one? Row subscript or the linear indexing vector. This is a column. Okay? So V1 is a row vector. So no matter what the form is, or the logical or the linear indexing vector, this always give you row vector. Okay? Oh, I mixed this part. If the input array is the column vector, output is a column vector, regardless of the form of the linear and the indexing vector. So V2 is the column, right? That's why the output form is always column vector, regardless of this form. Okay? Okay, but the difference is a matrix. Matrix. And then if the one is a row vector, right? That's why output is a row vector. Index 2 is this one, right? Column vector, output is a column vector. The same way in the linear indexing. This one, row output is a row vector. This one is the column vector. Okay, so here's another example of the logical indexing. Write a script to extract the all odd numbers in vector 1 and assign the resulting vector to the odd one. Okay. Do you understand this problem? Extract the all odd number and assign those numbers to the odd one. Okay. Let's write a script using the loop and then selection statement. Okay. You set up the loop range to the 1 to the number of the value. There's a number of value from the here. Okay. And then read the value. Read the value at II. And then test if this number is odd or even. Okay. If odd, you need to use the ram function. Ram is the a ram and then set the 2. We divide 2, if the remainder is 1, that is odd number. So this output is a 1. If this number is a 1, you can add the corresponding odd number to the odd one. Okay. So this one is I did not use the pre-allocation of the odd number, so I used this syntax. Okay. Then you will get odd number, all the odd number. Okay. Okay. How to perform this operation without using the loop statement? There are 3 components here. Okay. So I first array as an input of built-in function logical operator apply to vector and scalar logical indexing. Okay, so let's take a look at the first line. Ram function support the vector as an input. Vector as an input. So this operation is also the element-wise operation. That's why it gives you 1, 0. So here, if you divide by 2, the remainder is a 1 or 0. Okay. So that's why one location is the odd location, or the 0 location is the even location, right? And then here you need to pay closer attention to this vector, this one. Ram is not logical vector. Right? So we cannot use this one as an indexing vector. Okay? So that's why we need to convert it to the logical vector. The simple way is ram equal to 1. This one is equality operation applied to the vector and scalar, right? So that's why it gives you the same vector, but in this case it's double type. In this case it's a logical type. Make sense? Okay. Rather than this, you can simply write the script using typecasting. Back1 ram like this. Okay. This one is the same thing. Okay. Make sense? Then all these logical vector. Okay, so we plug in this logical vector to the vector 1. You can extract all the number. Okay,